G'day guys, this video is going to look at chapter 22 of Walding with the in-text questions. Probably going to try to get through questions 1 to 10 here, as that's the first section of in-text. So let's delve into it. Question 1 asks, describe the difference in behaviour between static electricity, direct current electricity and alternating current electricity in terms of flowing charges. Okay, so we want to make sure we're talking about flowing or moving charge there. Let's just draw up a 3-column heading here. So we've got static, we had DC, and we had AC. So in static electricity, think about, for example, you're scuffing your socks on the carpet and then you go and touch mum, dad, brother, sister, auntie, uncle, whatever, and you zap them. Or you're on the trampoline, again, socks on, it helps a lot for this, bouncing up and down, and then you touch your friend and psst, there's a zap that jumps between the two of you. So in terms of flowing charge, we get the build-up, then we get the release. And the release happens all at once. Okay, so there's no real flow, it's just it only flows when there's the opportunity to flow. It's not a steady flow. So you could build up quite a significant charge. In fact, if you go and scuff your feet with socks on a nylon carpet, so cotton socks on nylon, you can actually get a very significant voltage. You can be talking to thousands of volts. Just there's not much current, so it ends up being painful but not dangerous. Okay, let's talk about DC. So DC is what we started talking about in class, in that we have electrons in a current carrying a wire. There's a sea of electrons and they are moving. So they move at a constant rate in one direction. So DC is always in the same direction. AC, I've talked about a little bit. Remember, AC in this case, as the question says, stands for alternating current. So that means that the current is going to alternate, it's going to change direction all the time. So in the first second, it might say go that way, and then the second, it would turn around and go that way. And it just keep going forwards and back, forwards and backs, forwards and back, forwards and backs. And so the direction constantly changes. Direction constantly changes at a given frequency. So remember, frequency means how often something happens. In this case, we're talking about how often it changes. 5 Hz is fairly common, but you can get other frequencies as well. And if you're ever doing circuitry, that's one of the things you think about, like what frequency am I going to use. Alright, so there's just a brief overview of the three in terms of movement. Static charges don't move. They build up and they release when they get a chance, or if the voltage is high enough. DC just keeps moving at a constant speed in one direction. AC jiggles backwards and forwards constantly. Okay, so build up and release, constant movement, jiggling. Okay, so if you turn on your light and your light is DC, the electrons that say are at the switch will eventually hit the light. In an AC current, the electron at the switch is just going to go forward and then back, and then forward and then back, and it might gradually over time move around, but it's just really going to just oscillate around one spot. Okay, question 2. What is the voltage necessary to move 15 coulombs of charge through a conductor if the energy required is 80 joules? Okay, let's identify the numbers. We've got two numbers here. We've got 15 coulombs. That's a very large amount of charge, 15 coulombs. And we have 80 joules. 80 joules. Now remember, coulombs is a charge, and we give that the symbol Q. 80 joules in this case, we're talking about work being needed, so you could use E for energy, and about now you might be screaming in your brain, wait, we have E for electric field, now we've got E for energy? Yeah, sometimes unfortunately you might get the same letter being used for two different things, so just be careful, but do be aware. However, it may very well be called work. And if we have a look here, the last thing it asks is, well, what voltage do we need? So what is the voltage necessary? V. Okay. Now, so what we're basically saying is, how much work, how much energy do I have to put in to push a charge through with this much, or to push a charge with this much energy? Okay, so the voltage, remember, is the push. How strong are we actually going to push it? And we want to know, well, what is my if I need to give it this much work, okay, this much energy, then I've got this many charges, how much do I actually have to put in? Remember that a unit for voltage, we've already seen a formula for this where V equals, what is it, W over Q, or that work equals Q times V. We take the charge we care about, and we figure out how hard we're going to push it. That gives us the energy that's contained in that, and we can see that will match up here. We can rearrange. We'll get that volts equals work over charge equals 80 joules divided by 15. Let's see, that goes into 75 evenly, 5 left over, so it should be 5.3 volts. 1695, yep. Okay, question 3. A piece of metal conductor is estimated to contain 3 times 10 to the 22 electrons per meter of its length. If it carries a current of 1.5 amps, determine the average drift velocity of the electrons in the conductor. Okay, so we need a velocity. We need to know how fast these things are moving. We're told what the length containing electrons, and we're told a current. So let's identify what we've got here. We have 1.5 amperes, and that was equal to I for current. We want to know the electron density is, so I'm just going to go E minus density equals 3 times 10 to the 22 electrons per meter. Now, if we know how far it goes, we can work out the electrons in here. Remember, we know that therefore the amount of charge would equal, well, in that amount, 1.602. So that's an E minus, or Q of E minus, the charge of an electron, times 10 to the negative 19 coulombs. Sorry, not joules, coulombs. So that might be useful. Now, we defined current, we've defined the rate of conduction as I equals Q over T. And we can see we've got a Q maybe, we've definitely got a current. One question might be, well, what's the time we're going to use? Now, what I would do with something like this is that I would use a time of 1 second, because we want to work out the average drift velocity. Whatever time we use, we're going to have to divide it by that, because remember, velocity is meters per second. So let's just use 1 second. That way, I is going to be equal to Q. That's going to be nice and easy for us. So if we have a current of 1.5 amps, 1.5 amperes, what we're saying there really is that in 1 second, 1.5 coulombs goes past. Okay, so let T equal 1 second, therefore I equals Q, Q equals 1.5 coulombs of charge. And hey, look, now we've got 1.5 and we've got this. Okay, so current, we're saying that 1.5 coulombs of charge passes a point each second. We know how much charge is on one electron, so let's work that out in terms of electrons. So the number of electrons is going to equal 1.5 divided by, well, what's the charge of one electron? 1.602 times 10 to the negative 19. And that's going to give us 1.5 divided by 1.602 times 10 to the negative 19. 9.4 times 10 to the 18 electrons. Okay, it's just a number, it's not a counting number, it's not a unit, it's just a counting number. So what we've worked out there is that being as we knew the charge, the current, and we said let's let time equal 1 second. Okay? If we let time equal 2 seconds, then we would still end up with a number that would let us go, alright, well, this is what it's going to be for here. And then we'd end up with a Q of 3. And you'll find that the numbers will work out the same no matter what you let time do. You could let time equal 100, you'll still get the same answer. 1 just is easy because I don't have to do any math. Right. And by knowing that 1.5 coulombs of charge passes a point every second, and we know how much charge is on one electron, we've now worked out, well, this is how many electrons pass this point every second. Okay, that's a lot of electrons passing this point, but we know this is how many electrons are in 1 meter worth of thing. So if we can work out then, well, if there's this many electrons in 1 meter, how much space or how much length requires this many electrons? And I'll say that again. We know that that's the amount of electrons, and I'll draw that out. Let's draw 1 meter. So that's 1 meter. And we know that if we were to count up all the electrons in it, the number of electrons would equal, what's in the question, 3 times 10 to the 22. But we have 9.4 times 10 to the 18 electrons. We can see that number's a lot smaller than that. How small is it though? What is the actual length needed for that many electrons? Okay. And the way we're going to do that is I'm going to just divide this number by this number, and then we'll work out what this missing value, we'll just call it x is. It is a length, so x is pretty common for that. Because if 1 meter divided by x should be the same as this number divided by this, we're talking about proportions here. It's a fairly common math technique, and it will pop up a lot. So if this is divided by this is the same as this divided by this, then that divided by that is the same as that divided by that. The only reason I do that is I don't have to move my x's around and cross multiply and crap. It skips 2 steps in once basically. I'm going to write that as a formula. X divided by 1 is equal to 9.4 times 10 to the 18 divided by 3 times 10 to the 22. And I'll show you another way that we could check that in a second. Let's put that into calculators first. 9.4 times 10 to the 18 divided by 3 times 10 to the 22. We get an answer of 3 times 10 to the negative 4 meters. Okay, how did I know to do that divided by that? Why didn't I do that divided by that? Well, if we did do the reverse of that, so 3 times 10 to the 22 divided by 9.4 times 10 to the power of 18, we would get an answer of over 3,000 volts, or sorry, over 3,000 meters. So we'd be saying then, well, that's a lot bigger than 1 meter, but this number's a lot smaller. Okay? Think of it like this. If I have a room that I can fit 100 kids into, and I know that the room is, say, 20 meters squared, and then I go to another room, and I don't know how big it is, but I know I could only fit 50 kids into it, the room must be smaller than the original room. Here, I knew that 1 meter had this much, some unknown length had this much, that 10 to the 18 is a lot smaller than 10 to the 22, so my answer should be smaller than 1 meter. Okay, so we know now that 9.4 times 10 to the 18 electrons passes a point every second. In that amount of electrons is contained in 3 times 10 to the negative 4 meters. Now some of them are going to be very close, but at least one of them is going to be this far away, none of them will be further, they'll be that far away. So in this case, well, what's the velocity going to be equal to? The velocity is going to be equal to this length that the electrons travel in the time that they travel. what was the time? Time's back up here, 1 second. And so now we can say that velocity equals displacement over time equals 3 times 10 to the negative 4. It's on a straight line, so it'll be the same as distance, divided by 1. Well, that's easy. Equals 3 times 10 to the negative 4 meters per second. Now, that's a reasonably complicated question. I would give that around a B to an A standard type question, probably a B standard at this point, just because there are a few things in there, and the formulas are not obvious. This is mostly conceptual thinking your way through it. So that's a really good question to revisit and make sure you can puzzle it out yourself. Let's move on to question 4. Calculate the increase in potential produced by a cell if every 2.6 coulombs of charge passing through is supplied with 3.9 joules of energy. Okay, let's do the same thing as before. Let's write down our numbers. We have 2.6 coulombs and we have 3.9 joules. We know that this is coulomb, so it must be a charge, symbol Q. This is joules in work or energy, so let's give it the symbol W for work. Remember, work and energy are the same thing. And I'm trying to avoid giving you E's after E's because that would just be annoying. Question reads, calculate the increase in potential, okay, produced by a cell. A cell is another word for a battery, so we want V. Well, this just seems like what we did before, where we had V, Q, and W, so let's try that. Remember that V, so work equals Q times V, so V is going to equal to work divided by Q, 3.9 over 2.6, it's going to be 2.6, 1.5. This is question 4. Sorry, I was looking at question 5 in a second. Now, question 4, 1.5 volts, which is the correct answer. Okay, question 5. If you think, for this question, if you think back to the demonstration I did in class where I was running past Ben, I was slapping his hand, and I was slowing down, and I'd come back around to what I was saying was my battery, then I'd speed up again. That's what they're talking about here. We're taking a charge, we're giving it some energy, it goes off, it does work, it comes back with less energy. Question 5. A voltage of 120 volts is applied to a bulb whose resistance is 200 ohms. Okay, let's write down these values. So we have 120 volts, and we have 200 ohms. Okay, now ohms is the symbol for resistance, so capital R for resistance, and voltage is symbol V, so voltage. And part A of this question is asking us what is the current through the bulb. Current has the symbol I. So we've got V, we've got I, we've got R. This is Ohm's law, and so I equals V divided by R equals 120 over 200, which is what, 12 over 20 to 6 over 10, which equals 0.6 amps. Part B, how much charge, remember charge is electrons, or Q value here, flows through the bulb every hour. Okay, so we are asked about Q, and the question also says bulb every hour. That's a time there. Okay, it's a worded one, but it is a time. And so time in this case is going to equal 1 hour, which equals 60 minutes, which equals 3,600 seconds. Got to convert it to standard units. So we've got T, we're chasing Q, and we just solve for I, so we're probably going to need I. And we do. Remember our formula, I equals Q over T. So Q equals I times T. Dot there, so multiplication, equals 0.6 times 3,600 equals 2,160 coulombs of charge, right? Or 2.16 times 10 to the 3. I'd leave it like that though. I mean, 4 digits, not a big drama. Question 6. A pigeon stands on a 100 kilovolt high tension wire that carries 50 amps. If the line resistance is 2.0 times 10 to the negative 4 ohms per meter, calculate the voltage across the bird if its feet are 3 centimeters apart. What can you deduce about the likelihood of a pigeon being electrocuted? Well, you've all seen birds land on wires, so pretty much can say it's not going to be electrocuted. What we want to ask about now is the current, the voltage through the bird itself, because it's touching two spots, and so it's like basically constructing a circuit in parallel, which we haven't talked about yet. I know if you're watching this video straight away, however it is coming up. So let's first off do the same thing. We've got 100 kilovolts. 100 kilovolts, kilo is 10 to the 3. We have a 50 ampere. Okay. The line resistance, so the resistance equals 2.0 times 10 to the negative 4 ohms per meter squared. This is not the right unit. It's this per meter squared. So we're going to need to get rid of that per meter squared. So we're going to need a distance, because distance is meters. If we multiply something with meters times something with ohms per meter squared, ohms per meter, I think I said square a few times then, it'll cancel the meters. Okay, so if I do ohms per meter multiplied by meter, I get ohms. Okay, this is a little bit of basic dimensional analysis, might be worthwhile. So let's give some symbols. We've got voltage, we've got current, we need a distance, okay, because that's what the formulas, the units are telling us we need, and we're told it's 3 centimeters apart. 3 times 10 to the negative 2 meters. So we can see, well, if I multiply these two together, I'm going to get rid of that meters, and I'm going to get just the resistance across a small stretch. We've got the current through the whole thing, and we've got the voltage across the whole thing. Okay, so let's see what we can work out here. First off, let's work out a decent R. The R is going to equal 2.0 times 10 to the negative 4 multiplied by 3 times 10 to the negative 2 equals, let's work that out, 2 times 10 to the negative 4 times 3 times 10 to the negative 2 gives us, I could do that in my head, 10 to the negative 6 ohms. There's our resistance, that's good. So that's the total amount of resistance from one foot to the other foot, or at least the wire from one foot to the other foot. Let's work out the voltage just across that small distance. I know we've got the voltage for the entire wire, but let's work out the voltage of just that small amount of wire. Still going to use the same formula, V equals IR. Okay. We've got I equals 50 amps times 6 times 10 to the negative 6 equals 50 times 6 to the negative 6 gives us 3 times 10 to the negative 4, which would equal, and we've got here 30 millivolts, and yes, that would be equal to 30 millivolts. 30 millivolts of current is tiny, it's not going to get electrocuted. So partly why the bird doesn't die when it perches on the thing. If it hits 2 lines, we know it's going to die. If it perches on just 1 line, the voltage pushing into the bird is very small. Okay? And it depends on what the bird's resistance is. Maybe their feet have some good resistance to electricity. If the bird had further apart, the voltage would be higher, because the distance would be higher as well, and the resistance would end up being higher. So how big the animal is actually does help a little bit in this case. That being said, I mean, you have to have something pretty big to, touch it in 2 points and end up with huge voltage. It's going to arc into it. So 30 millivolts, that bird is safe. You're asked to design the electrical parts of an electric toaster. Describe the nature of the electrical conductors you might use. So, the hint I'd give you for this is that what we're really talking about is the bits that can heat up the bread and get nice and red hot. So we want to think about the nature of those electrical conductors. Conductors heat up when electrons hit into the atoms and lose some energy. That's resistance. So things hit into it. So if I wanted to get red hot, I wanted to gain as much energy as quickly as possible. I want something with a high resistance so that as I'm smacking electrons through this wire, they're going to be hitting the wire quite a lot, and then we end up with a nice red hot toaster element. Okay? If it was a low resistance, it would just go straight through. The electron wouldn't hit, or the charge wouldn't hit the atoms inside the resistor, and so because of that, there'd be no energy transference. No energy transference means it takes a lot longer to warm up, and is sitting there staring at cold bread for a couple of hours, which I don't think we want for breakfast. Okay, so high resistance equals quick heating. Okay, nice and simple and straightforward. Question 8. The resistance of a certain metal conductor A is found to be 0.36 ohms at 25 degrees Celsius. Remember that as you make it hotter, the resistance does increase. If you found another conductor B made of the same material with differing characteristics as shown below, calculate in each case the new resistance value of B compared with A. Okay, so we've got two things that made of the same material, but they physically look different. Okay. Conductor B is 3 times longer than A, and the formula we want to use, the resistance is equal to rho times length over area, length over cross-sectional area. So as length goes up, resistance goes up. As the area gets wider, goes up, the resistance goes down, and then there's this just conductivity thing. We don't care about that because it's the same metal. Okay, so that's not going to affect it. It's the length and the area and the temperature that matters here. So L1 or L2 equals 3 times L1. So we're multiplying L1 by 3. So if I made that number 3 times bigger, we can see that R is going to end up being 3 times bigger. So the original ohmage was 0.36. So R1 equals 0.36 ohms. R2 equals 3 times R1 equals 0.36 times 3, 1.08 ohms. Alright, so it's getting bigger. Let's go to B. So that was part A. Part B. Part B says the conductor is only half the cross-sectional area of A. So we're making the statement then that area 2 equals area 1 divided by 2. And if we were to put that in that formula, we would see then that if you're dividing by a half on the bottom, it's the same thing as multiplying by 2. There's some basic fraction stuff to practice. So therefore, resistance 2 would equal 2 times resistance 1 equals 0.72 ohms. Okay, so because it is reduced by half, we end up with our what's what I'm looking for? With our resistance here doubling. And let's go to C. Conductor B has just been taken from an oven operating at 350 degrees Celsius. Good news is we can say, yep, it's going to be hotter. Problem is, there is nothing in here about what type of material it actually is. That hasn't been provided with us. So we would need to look up some information about resistance at a basis of temperature. Okay? There is the temperature coefficient, and that's back on table 475, where it gives us a coefficient which tells us that, how much it increases by, what the resistance increases by. Now, there is a formula given to us on a previous page that the resistance at a temperature equals the original resistance, which is based at 0 degrees. Okay, so that's one's at 0 degrees Celsius. 1 plus alpha change in temperature. Okay, and we've got here the resistivity at 0 degrees from the look of it. No, that's the rho value. It's not really giving us a 0 value for copper anyway. We've got the temperature coefficient. I'll just use copper because copper is the most common thing there. Let's scroll back, see if we can find a resistivity of copper at 0. Doesn't look to be there. There was an example previously up. It says from table 22, resistivity of copper is over at 0 degrees. Where's that from? 22.2. Oh, okay, so that resistivity is the number we want. No, that's a completely different thing. I guess that's a very bad tape or a very bad explanation of where they got the numbers from. However, if we go back, if you go back up to page 476, the solution for that example there tells us a statement: the resistivity for copper is 1.7 times 10 to the negative 8 ohms per meter at 0 degrees Celsius. Okay. Actually, no, we can't use that because we want the original resistance. We don't know anything about it in terms of length or area, so we can't really substitute. So, let's take a quick guesstimate. They do give us an answer in the text, however, I don't believe it's something that we can really work out accurately and authentically. We look at this, we see, well, if temperature changes, that's going to change. It's going to change in proportion to some constant. That doesn't really matter, it just slows it down or speeds it up. We add 1 to it because that way it's always going to be an increasing number or a decreasing number depending on what sign delta t is. If delta t comes out positive, that's above 1, so therefore that increases. If that's below 1, so if that's a negative number, then that whole thing will come out below 1 and this number will reduce in proportion. So if we can see that increase if delta t is positive, then RT increases. The actual answer that they've given us here is that the resistance would equal 0.8. We could certainly work back to figure out what they've actually used for R0. I don't really think it's worthwhile, to be honest. Yeah. I mean, we could take a difference of temperature of just 325 degrees Celsius, because we've got our starting at 25 and ending at 350. We could try with that. However, I think we can see that, well, if temperature goes up, it's going to fight back more. We'll talk about that in class. Question 8. Resistance of a certain metal conductor. No, sorry, that was the one I just did. Question 9. Sleepy. Question 9. Refer to figure 22.10. Figure 22.10 is back a couple of pages. So let's find that. Figure 22.10. 22.10. And, okay, we've got a circuit. I'm going to draw this circuit. We have a battery. We have an ammeter that measures current. We have a resistor. We don't have any information about the resistance on it. That then connects back to here, and we have a voltmeter that is measuring the voltage across the resistor. It's measuring how much the push is on this side compared to this side. Now, current always flows from positive back to negative. And we'll see that as we go through circuits. However, no problem in me telling you now. Now, where was it? Too far. There we go. Okay. Refer to that. The students set up the experimental apparatus and found the following results as tabulated. Plot a current versus voltage graph and determine the value of the resistance at all points. Describe what you find. Is the resistor ohmic in its characteristics? So we'll get to that word ohmic in a second. We've got here current and voltage. We can see that at voltage is 0, current is 0, which is what we kind of expect. And then we've got our numbers. Now, I'm actually going to do this in Excel, so you won't be able to see it, but I will draw what my graph looks like after I've done it. I would recommend you pause this here, graph it yourself in Excel on your graphics calculator. However, you need to do something. Now, it says current versus voltage. That tells me current is going to be on the on the y-axis, while voltage is going to be on the x-axis. As I look at these numbers, the very first thing I notice is that voltage should be on the x-axis, current will be on the y-axis. As we go through this, we see that voltage is going up in 2222, so that's not a problem. But current acts a bit weird around the 4 volt mark. I wonder if it should have been 0.025. Let me check the errata on this. We're in chapter 22. Chapter 22, question 9. Table has the current. Okay, yep. So that is an error there. So it should be 0.025. And always good to look at these and say, well, what this number doesn't sort of follow the pattern I'm kind of expecting here. 0, 2, 4, 6, 8, 10, 12. And let's do a graph. I'm going to put my x value as voltage, and I'm going to put my y value as current, and I'm going to add a trend line with the r squared. And by doing that, it looks like I have a pretty close to straight line. So I have currently voltage down here, current on this side, and I have a nearly straight line with an r squared equaling 0.99. That tells me it's pretty much a straight line. There's just a little bit of variation probably from how they figured out the numbers here with a bit of rounding. We need to determine the resistance at all points. Okay. Because it's almost a straight line, we don't really need to calculate every one. We can get a general resistance. And remember, if we look at the formula, V equals IR, or if we go the other way, sorry, I equals V over R, I equals V over R, we can see, well, if Y equals mx, and we have y is equal to I, and x is equal to v, then we have I equals mv. And if we look at these two formulas, we can see, well, v is not times r, it's divided by r. So that means the gradient m must equal 1 over r. So if I take whatever my gradient is, and then I inverse it, and if I display the equation, I get the equation y equals 0.0064 x minus 0.0002. I don't care about the 0.002 in the end because it is a matter of just an intercept. All I really care about is that gradient, that number in front of my x. And we just said, well, m is equal to 1 over the gradient. Let's work that out. Equals 1 divided by 0.0064. We get that r equals 1 over 0.0064 equals 156.25 ohms. Okay. Now if you calculate every single one of those, and you can do that, you've got all these data points, there's no reason you couldn't calculate this thing by just going, well, if V equals IR, then V divided by I should equal resistance. And that's from the formula. So voltage divided by current equals the thing. And I'm just going to do all those quickly in Excel. That's why I like Excel. We get that the first voltage is, so first resistance 153, then 160, 150, 160, 166.67, 150. So it's always varying around that point. Okay. And I've just got you an average resistance there. Describe what you find. It's a straight line, we would say that. Is the resistor ohmic in its characteristics? Explain. So we need to know what the word ohmic means. Now, if we scroll back up through the text, you should find a definition of the word ohmic. And so let's have a look it up. So I'm going to look up Google. Let's go for resistor. So, very first thing from Quora, which is generally pretty decent, sometimes very confusing, but generally it's fairly good quality responses. Ohmic resistors are those resistors that have a constant resistance. In other words, they follow Ohm's law. Now, if we look at our graph, while there was a bit of bounciness in it, it pretty much is always the same. That tells me it follows Ohm's law. It's always got the same resistors, okay? And then if you plot it, you should get a straight line. So because V against I is straight, therefore ohmic. Nice and straightforward, nice and easy. We've looked at the data, we've made an interpretation of what it is. Okay, and we've said why we're saying what it is. Alright, last question for this video, question 10. Consider figure 22.13 showing an EMF source. An EMF source is just another word for battery, and its internal resistance connected to two series resistors of value 15 ohms. Calculate the readings on the circuit meters shown. Okay, let's draw this circuit up and we'll identify what we're trying to find. We have a battery of 12 volts with resistance equaling 0.4 ohms. We have a ammeter around to a resistor. Now they've used a jagged line. I'm just going to do a square because it's easier. Both are acceptable. Around to, so that should be 15 ohms. Another resistor of 15 ohms before going back to where the circuit starts. And remember, the circuit always goes direction of the long line around to the short line. We want to calculate the readings on the circuit meter shown. So we want to know, oops, sorry, I missed a voltmeter across the battery. We want to know what is this V going to say, and probably won't say 12 volts, and what is this ammeter going to say? I'm going to have to work that out. So, we are still dealing with Ohm's law here. It's nothing different there. If we, that's the best way to talk about it. Let's look at the total resistance of the circuit. Okay, so let's look at the total resistance of the circuit. Because these things are in series, we have this bit, and then this bit, and then this bit, and then we come back. The total resistance equals 15 plus 15 plus 0.4, and that's going to equal 30.4. That'll let us work out the current, because we know the voltage. The voltage equals 12 volts, and we can work out the current. I equals V over R equals 12 divided by 30.4. And we plug that in, 12 divided by 30.4 gives me around 0.4 amps. Now if we double check our answer there, we see that should be 0.39. So I rounded up, but so instead of rounding up, let's put that at the correct one. 0.39 amperes of current. Okay, so that's telling us that if we were to work out in electrons, we could figure out how many electrons are getting pushed through every second. But in terms of amperes and current, it's 0.39 coulombs per second. We want to know what is the voltage across the battery. Okay, that's not 12 volts. The reason is because some of that push is getting lost to the internal resistance of the battery. The way that we can work this out is by knowing the resistance equals 0.4, and we know that the current flowing into it is equal to 0.39, we could use those to work out the voltage going into it. Okay, the answer gives us that it should be 11.8. So we can't just take 12 and subtract 0.4 from it. There may be another formula for internal resistance of a battery. Okay, yep, so if we go back up to page 477, the voltage inside of it is equal to the electromotive force, the 12 volts, how much push it actually gives, minus the current that flows through it, times the internal resistance. Being as we don't have, we had to work out the current anyway, so it's good we've already got that, but now we can work out what the drop is going to be. So let's work that out. The voltage, how much is getting used, equals IR equals 0.39 times 0.4, sorry. Is it 0.4? 0.4. 0.4 equals 0.39 times 0.4, 0.156, so around, they've rounded it off to 2 from the look of it because there is only one significant figure here, so we have to round that to 0.2. Okay. Let's do 0.16 just for the sake of it, just to give it a bit of extra precision. That's the voltage drop that is used, that's the voltage that gets used up by the battery just doing its job. So if it has 12 volts, so voltage equals 12 volts, we're going to take away that 0.16 because it's not going to go anywhere else. Okay? It's going to only go to the battery, and that gives us an answer of around 11.84, which we could round down equals 11.8 volts, or that's equal to the last form. Oh yeah, just volts. Okay. So this has looked at questions 1 to 10 of chapter 22. We've looked at a bit about how we need to push electrical circuits. We've also looked at applying some basic Ohm's law to some different circuit designs. Next video we'll look at question 11, 12 and probably onwards from there. There's a couple of small question sets coming up and we'll see what we do from there. Alright, any questions? See me in class. Otherwise, have a good night, guys.